Okay, so this was N1 that we got out. Let's go and let's do N2, and then we can do N3. Okay, so let's make sure we apply the same principles to N2, and we learn the same principles. Okay, so I'm going to leave that there, and now let's say node 2. Okay, information Q2 we want to propagate over the spatial domain, but we want to make sure that N2 is such that if I evaluate it at this place here, I only recover value of Q2, so I want to make sure N2 evaluates to 1 when I have it here. Because remember again, the contribution to the displacement field from node 2 will be U2. It's a function of psi. It will be some function N2 f psi multiplied by Q2. The Q2 is what we'll solve for, so I want to make sure this evaluates to 1. Okay, so N2 at psi equals to 1. I want to make sure it evaluates to 1. N2, don't want to have it to have a contribution at this node or at this node. So at psi equals to 0, I want to make sure it's 0, and N2 at psi equals to minus 1, I want to make sure it's also 0. Okay, so these again are my roots. I can construct this. This equation from its roots. Say so. N2 should have the form psi multiplied by 1 plus psi. Yeah. So this is. I just take it to this side and get my root. So again, I can just show you. If I plug in psi equals to 0, this expression will be 0. If I plug in psi equals to minus 1, 1 minus 1 is 0. That's beautiful. The only thing is I need to check is if I evaluate psi at, so this is checked, and this is checked, this is not checked yet. If I evaluate psi at equals to 1, then this is 1, and this is 1 plus 1, which this evaluates to a 2. And now if I divide by that, I get a half. This is my expression. If I now plug in 1, it's 1. 1 plus 1 is 2, divide by 2 is just 1. Now I've got what I wanted. Okay, so there's my N2 expression of psi. A half psi 1 plus psi. Okay, and then yeah, this is going like a quick, so I can quickly do the third one, N3 as well. So this one. So there's my third expression I'm going to do now. N3. Node 3's contribution, so let's look at N3 psi. Want to make sure that N3, you want to evaluate it at psi equals to 0, I recover a 1. Yeah, because only contribution of Q3 at this node. I want to make sure that N3 evaluate at psi equals to minus 1. It evaluates to 0. N3 at psi equals to 1 evaluates to 0. Okay, again my roots. From the roots I can say fantastic. N3 should have the form 1 minus psi 1 plus psi, and we can check. If I plug in minus 1, then 1 minus 1 is 0. If I plug in 1, 1 minus 1 is 0. So this will evaluate towards 0. Now I need to just say if I plug in here psi equals to 0, what happens? 0, this becomes a 1, 0, this becomes a 1. Done. Okay, so I can just say 1 divided by 1. Okay, so N3 is that. One minus psi, 1 plus psi. Okay, there's my shape function that I've got. And what I have here now is essentially the 3 shape functions associated with node 1, node 2, and node 3. And now to round this off, I can say the following. Okay. Yeah, 4 minutes, that's good. We're still doing good on time. Is I can say my displacement field, which I'll write now as a function of psi. Okay, I can write as follows: N1 multiplied by its unknown, N2 multiplied by its unknown, N3 multiplied by its unknown. And there's my displacement field here. And you can go and check for yourself and see the beauty of this is if I evaluate at psi equals to minus 1, I recover the value of Q1. If I evaluate at psi equals to 1, I recover the value of Q2, and if I evaluate at psi equals to 0, I recover the value of Q3. And so here I've got an example of how we're going to be thinking about displacement fields using the finite element method approach. Okay,